Hi, I'm Prof L. Welcome to Chemistry Matters. And today we're going to be talking about quantum numbers. Now, in another video that I've done, we introduced the concept of quantum numbers, although we didn't actually call them that. So, we had an equation that said that En is equal to minus 2.18 times 10 to the minus 18 joules over n squared. And this equation tells you the energy of any of the energy levels in the hydrogen atom. Now, this n here we said was any integer. N could be 1, 2, 3, ... as I said, all the way up to infinity. N is actually a quantum number, and it has a special name. N is in fact called the principal quantum number. In fact, there are two other quantum numbers that we're going to be looking at today, and without further ado, let's get into them. L is a thing called the azimuthal quantum number. There's a mouthful. And a thing called ML, and that is called the magnetic quantum number. Quantum numbers are so called because they cannot actually have any particular value that they want. Remember, we talked about quantization in another video, the fact that atoms can't have any particular energy that they want. So quantum numbers also have restrictions upon their particular values. And so we're going to talk about that today, and we're going to talk about what this means in terms of atoms themselves. How are these quantum numbers, these N, L, and ML, how are they actually related to atoms? What do they mean physically, I guess, if we can sort of ask that question. So let's start off by looking at the possible values that these quantum numbers can have. We've already seen the principal quantum number. We started off and we said, okay, here is the principal quantum number in this equation, N. And N could have the value of positive integers, okay? 1, 2, 3, all the way to infinity. So those are the possible values of N. It could be 1, 2, 3, ... all up in integer steps, all the way up to infinity. Now L, the value of L now depends on the value of N, okay? And this is where the whole quantization thing comes into it. L can't have any value that it wants. Its values are dependent on what the value of N is. So L can equal 0, 1, 2, 3, ... all the way up to whatever the value of N minus 1 is. So there is your dependence of L on N, the principal quantum number. It can be any integer all the way up, including 0, all the way up to the value of N minus 1, okay? And ML, the magnetic quantum number, can be negative L, all the way up to 0 in integer steps, all the way up to plus L, positive L. So those are the values that each of these particular quantum numbers can have, N, L, and ML. So, learn these rules. They are important. You need to know these. And now let's go ahead and actually use these particular restrictions on the values to figure out what values of sets of these quantum numbers can be, okay? We're going to use these three quantum numbers together. And so therefore, we're going to end up with, I guess, three values, and we're going to work out the possible allowed values that these quantum numbers can have. So remember those rules, and let's start by saying, okay, we're going to take an atom for which N equals 1. We'll start off there. What then can the value of L be for that? Okay, so we think back to our rules, and we said L could be, okay, it could be 0, 1, 2, 3, blah, 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 all the way up to N minus 1. So if N is equal to 1, L has only got one possible value, hasn't it? L can only be 0 because that can only go in integer steps from 0 all the way up to n minus 1. If n is 1, n minus 1 is 0, L has to be 0. What about ML? ML, in this case, remember, goes from negative L to positive L. If L is equal to 0, the only value that ML can have is 0. Those are the only possible sets of values for a system where n is equal to 1. If n is equal to 1, you've only got this set of quantum numbers and that's it. There's no other possibilities. And actually satisfy yourselves that that's the case. Let's then go to n equals 2. So n equals 2, what can L be? So again, we use our rules. L can be 0, 1, 2, blah, 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 all the way up to n minus 1. So if n is equal to 2, n minus 1 is equal to 1. So L could be 0, and L could also be 1, couldn't it? Because it can have any value all the way from 0 up to n minus 1. Let's do these in 2 steps then. If n equals 2, L could be 0, and if L is 0, ML has to be, well, there's only one possible value it can be, because remember, ML goes from negative L to positive L. If L is 0, ML is 0. If L is equal to 1, on the other hand, what can ML be? Okay, L equals 1, ML goes from negative L in integer steps up to positive L. So ML can be negative 1, 0, and positive 1. Okay, so a little bit more complex for the situation with n equals 2. Okay, we've got now more than one set of quantum numbers that we had for n equals 1. Let's go to n equals 3. Again, what could L be? L, 0, 1, 2, blah, 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 all the way up to n minus 1. So L could equal 0, L could equal 1, and L could equal 2, which is n minus 1. So if L equals 0, we've already seen this, ML is going to be 0. If L equals 1, we've already seen this. ML can be negative 1, 0, 1. The one we haven't seen is what happens with L equals 2. ML can go from negative L to positive L, negative 2, negative 1, 0, 1, and 2. And so we've got a whole lot more sets now of possible quantum numbers for n equals 3. We're going to stop there. We could keep going quite happily. And now we're going to find out what all of these things mean. What do all of these combinations, these quantum numbers, actually correspond to? That's the question that hopefully we are going to answer. And I guess we actually have a one-word answer for that. They correspond to orbitals. Now, what's the definition of an orbital? An orbital is just a region of space where you've got a probability of finding an electron. That's what we mean by orbitals in atoms. And each of these combinations of quantum numbers correspond to what we're going to call an atomic orbital, an orbital within an atom. Right, so we said that n was called the principal quantum number. It also has another name, and that is the orbital energy quantum number. L we call the azimuthal quantum number. That also has another name, and that is the orbital shape quantum number. And ML we call the magnetic quantum number. It's also got another name, and that is the orbital orientation quantum number. N defines the energy of an orbital. L defines the shape of a particular orbital, and ML defines the orientation, the possible orientations of particular orbitals. Let's then maybe have a look at some of the shapes of these orbitals, okay? So what we find is that orbitals come in different shapes, and in the first instance, we get these types of orbitals. These are spheres, and we call these s orbitals. They are spherical in shape, and they come in groups of 1. Here we have things called p orbitals. They look like dumbbells, and they come in groups of 3. And here we have things called d orbitals. they sort of kind of look like four-leaf clovers sort of things, and they come in groups of 5. Now, let's explain all of those observations in terms of quantum numbers, okay? We said that we have got groups of quantum numbers 1, 0, 0, okay? That corresponds to an s orbital, and in fact it corresponds to what we're going to call a 1s orbital. The 1 comes from the fact that the principal quantum number is 1. The s comes from the fact that the orbital shape quantum number is 0. Every time we have L equals 0, we've got an s orbital. And the 0 for the orbital orientation says that you've really only got one way of putting a sphere in space. We're going to call that a 1s orbital. We also had this set of quantum numbers, and that corresponds to what we're going to call now a 2s orbital. 2 coming from the principal quantum number, 0 the orbital shape, saying it's an s orbital, and the orientation, you've only got one possible orientation. We then had a situation where we had 3 types of quantum numbers that were pretty similar: 2, 1, 1, 2, 1, 0, and 2, 1, minus 1. We're going to group those into 3, and we're going to call these p orbitals. This is a 2p orbital, this is a 2p orbital, this is a 2p orbital. 2 again from the principal quantum number, 1 now coming from the orbital shape quantum number, saying that that is a p orbital. And these groups, or this group of 3 now, differs only in the magnetic quantum number or the orbital orientation quantum number, okay? So in other words, we're saying that these p orbitals, these ones that look like dumbbells, can be oriented 3 ways in space. And we're going to call that a 2px, and we're going to call that a 2py, and we're going to call that a 2pz orbital, okay? So in other words, as I said before, s orbitals come in groups of 1s, p orbitals come in groups of 3s, and d orbitals come in groups of 5. So let's very just quickly show what happens with the n equals 3. We derived these, we said that, okay, you can have a 3, 0, 0, that's going to be a 3s orbital. A 3, 1, 1, we would have a 3, 1, 0, and we would have a 3, 1, negative 1, and they would be 3p orbitals, a 3px, a 3py, and a 3pz. Now, in addition, we've got a 3, 2, 2, and a 3, 2, 1, and a 3, 2, 0, and a 3, 2, negative 1, and a 3, 2, negative 2. Now, the 2 corresponds to a d orbital. And these 5 different values of the orbital orientation quantum number tell us there are 5 different orientations of these d orbitals. They're given special names. So this is going to be a 3D type of orbital. All of these are going to be 3D orbitals. These have special names. So this will be a 3DXY, a 3DXZ, a 3DYZ, a 3dx squared minus y squared, and a 3dz squared. Don't worry too much about where these came from. The important fact is there's 5 of these, and they have got different orientations in space. So here are your quantum numbers. Here are the corresponding orbitals. And we're going to finish off now by showing you what these look like on an energy level diagram. We're going to start off with a 1s orbital down here. We are then going to have, at a higher energy, we're going to have a 2s orbital. And we're going to have 3 2p orbitals. And then we're going up to a 3s orbital. And we're going to have 3 3p orbitals. And we're going to have 1, 2, 3, 4, 5 3d orbitals. Remember I said s orbitals come in groups of 1, p orbitals come in groups of 3, d orbitals come in groups of 5. That's enough for you to know at the moment. We can get into f orbitals, which come in groups of 7. We could go to g orbitals, which have groups of 9, but we're not going to worry about that. This is plenty for you to be going on with at the moment, okay? So what we have drawn here is essentially the energy level diagram for a hydrogen atom. And this hydrogen atom contains a 1s orbital, a 2s orbital, a 3s orbital. It's got 3 lots of 2p orbitals, 3 lots of 3p orbitals, 5 lots here of 3d orbitals. And this is a really, really important diagram because this shows us what is actually happening when hydrogen atoms are being excited by absorbing photons, and what happens when they are giving out energy, spitting out photons and going from higher energy levels to lower energy levels. The take-home message, each of these orbitals is defined completely by a set of 3 quantum numbers. We went through all of those ones there. You can, as a homework exercise, I guess, go and assign each set of 3 quantum numbers to each of these orbitals and see how you do. Hopefully this has taught you something about quantum numbers and their relationship to orbitals, and we'll see you next time.